KD tree is a data structure useful when organizing data by several criteria all at once. Consider an example where you have a set of points on a two-dimensional plane. Now, suppose you are asked to find the nearest neighbor of some target point. What data structure would you use to store these points to be able to solve that problem? A naive approach would be to perhaps store the points in an array sorted by one of the properties, such as the x-coordinate. Then you could easily do binary search to find a point with the closest x-coordinate, but unfortunately, you'd still not necessarily be any closer to finding the point where the y-coordinate is also nearby. To convince yourself of it, just think of the case where all of the points share the same x-coordinate. Clearly, you'd have to examine every single point one by one to find the nearest neighbor of the target point. Hello and welcome to StableSort. KD tree data structure is very much like a regular binary search tree, except instead of holding just one value in every node, it holds k values. When traversing a KD tree, we cycle through the index to the values list based on the depth of a particular node. The k in the name KD tree refers to the number of properties that each data point has. In our example, since it's a two-dimensional plane, we have exactly two properties, the x-coordinate and the y-coordinate. So the root node starts off arbitrarily picking one of those. Let's suppose it's the x-coordinate. Then its children, the second level, alternate to using the y-coordinate. The grandchildren nodes cycle back to using the x-coordinate, and so on. When inserting a new node, just like in a typical binary search tree, we compare the node's value and go left if it's smaller, right if it's bigger. It's just that as we go deeper and deeper down the tree, we keep alternating between using the x and the y values in the comparison. Note that in our example, since we started with comparing the x values, the y values were ignored, and as a consequence, the second layer nodes break the binary search tree rule where all the nodes less than the root are on the left side and vice versa. But amazingly, it turns out that this is okay. The magic here is that we can check for this inconsistency on the way back when unwinding the recursion. Visually, you can think of the root node dividing the xy plane into left and right sides, since we decided to start off with using the x-coordinate. Then the next point will fall into either the left or the right side, and in turn, divide that side into top and bottom sections. So as more and more nodes are inserted into the tree, each point splits parent section into two subsections, alternating between splitting the section into left and right versus top and bottom. Suppose our target point is 9, 4, and our goal is to find its nearest neighbor. So we walk down the tree and keep calculating the shortest distance found so far. Note that on the way down, we missed the point 10, 2. This happened because when comparing with the second node of the tree, point 13, 3, the y-coordinate was smaller than the y-coordinate of our target point, 9, 4, so we traversed the tree by going right. Once we have gone as far down as we can, we then recurse back as you would in a regular binary tree search. We do have a candidate closest neighbor, but there is a possibility of a closer point still. Think of the shortest distance as a line going from the target point to the candidate point. Let's call this line R. This line is probably going to be at some random diagonal angle. But if the line directly perpendicular to the section that we chose not to visit when recursing down is shorter, then there's a chance that that section may have a closer point. So this is where the magic happens. As we recurse back, we also calculate the distance to the section that we did not visit. If that distance, let's call it R prime, is smaller than the best distance found so far, then we traverse into that section as well. But note that this does not mean that we visit every node in the tree. If the height of the tree is h, then at most we'll visit 2h nodes. In other words, this is still a logarithmic search in respect to the number of nodes in the tree. Here's a pseudocode for the nearest neighbor function. we mod the depth of the node by the number of dimensions that the tree uses. So as we go down the tree, the depth is incremented, but mod operation cycles through the values that are being compared. Choosing which branch to follow is very much like a regular binary tree search. But on the way out of the recursion, we check if the radius is greater than the distance to the other section of the plane. That's the magic line. Just a couple of final notes. The closest subroutine simply chooses between two passed-in nodes without recursing any further. And we don't bother taking the square root of the distances and just compare the distances squared so as to save some CPU cycles. For the full source code, see the link in the description. So far in our example, we've been using a two-dimensional plane, but the methodology works equally well in higher dimensions. Each node would still have a left and a right branch, but the number of values in each node could be arbitrarily large. Suppose you are designing a database for a hospital that keeps track of each patient's blood type, white blood cell count, and blood pressure. Then a new patient comes in with an unknown illness. Using a KD tree, you would be able to quickly select one or even a set of patients that share similar properties. These would be the nearest neighbors, with a higher likelihood of having a similar illness. Thank you for watching. I hope you enjoyed this video. Please subscribe to support this channel, and I'll see you in the next one.